So looking at x is equal to r cosine theta, if we want to take the derivative with respect to theta, if the change in x over change in theta is bigger than 0, then your function is moving to the right because that's your x direction. We can do the same thing with y. We know y is equal to r sine theta. So if we take the derivative with respect to theta of y, and that's bigger than 0, then we know it's moving up. The other one we can do is right away just do dr d theta, and that's telling us how the curve is moving towards or away from the origin. The slope of the tangent line is given by this, just dy dx. Now, if you notice, if I multiply instead of divide by dx d theta, if I went through and multiplied by d theta dx, the d thetas cancel. The other things that we have is that if we have, again, this tangent line, if we want to know where it's horizontal, a horizontal tangent line, this top would be equal to 0, provided the bottom is not. If we want a vertical tangent line, then we need this one to be equal to 0, the denominator. Again, assuming that the top is not. If both the top and bottom are equal to 0, then it's probably going to be a cusp or not differentiable right there. So looking at this, first thing we do is x is equal to r cosine theta, y is equal to r sine theta. They've told us what r is, so I went through and substituted that. I thought it'd be easier to distribute this. So when I take the derivative cosine, it's minus sine. Then you have to do the power rule, so 2 cosine theta, then chain rule, the derivative of the inside. And that leaves us with, if we can factor out a sine theta on both of them, I actually factored out a negative sine theta and divided by it. So if these two things multiply to be equal to 0, either sine is equal to 0 or cosine theta is equal to negative 1/2. The places sine are 0 and pi, and cosine's negative 1/2 at both those points. So those should be all things that have to do with a vertical tangent line. All right, if we're looking at the horizontal tangent lines, we look at the y. So same thing, I distributed. I took the derivative. Now, in order to simplify this, I saw I had mostly cosines, but this one sine squared. So I said, well, I know sine squared is 1 minus cosine squared. So I kind of changed that, rearranged it, put my quadratic first, factored it. So either cosine theta is equal to 1/2, which will give you pi over 3 and 5 pi over 3, or cosine theta is equal to negative 1, and that happens at pi. Well, notice I have pi over here and pi over there, so that guy's gone. We know we have a vertical tangent line at 0. Look at right here at theta equals 0. We have a vertical tangent line. At 2 pi over 3, right here, we have a vertical tangent line. At 4 pi over 3, we have a vertical tangent line. These are horizontal ones, so at pi over 3 would be about right here. It's got a horizontal tangent line, and 5 pi over 3. So what happened at pi? Notice right there at pi, there's that cusp. It wasn't differentiable there. Remember, it's not differentiable when there's a sharp turn. So I think this was a nice picture that you could understand the difference between when it's inconclusive and doesn't tell you what it needs to tell you. The next thing, I want you to find and interpret all these different things. And again, we're going to use that same r value, which was 1 plus cosine theta, or whatever it was up there. So I take the derivatives, and I notice that dx d theta is positive, so it moves to the right. dy d theta at pi over 3 is 0. It's not moving up nor down. And dr d theta at pi over 3, it's moving towards the origin. So let's look at what that is. So here's our graph up here. So at pi over 3. So here's where we were at pi over 3. We knew that was a maximum for our graph because that was where our horizontal tangent line was. And as I'm moving here, I'm moving to the left. At this point, I'm neither moving up nor down because I'm changing directions. And I'm going to start moving closer to the origin because it's going closer to r. It's closer to 0, 0. Next thing it wanted was the tangent line. So if we want the tangent line, the first thing you need to do is find the slope. But remember, we just did that. We just found the dy dx. We found dy d theta was 0 at pi over 3. Dx d theta is root 3, so 0. So that is a horizontal tangent line. If it's a horizontal tangent line, we're only looking at the y value. So the y value at pi over 3 is 3 root 3 over 4. Tangent lines at the pole. So here's our rows. Remember, that's the length of the petal. This tells you how many petals. Remember, we think of this when we graph it as you'd have 3 theta here, 0, pi halves. So 0 and pi over 6 are going to be your important numbers. Something's going to happen every pi over 6. So here's where it's 0, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. So again, it wants us to find dy dx. So I'm going to first find dy d theta, and then find dx d theta. And they want us to calculate these slopes at these different points. So I went ahead and calculated dy d theta at 0, dy d theta at pi over 3, so on and so forth, and then I just took the ratio. So dy dx at theta equals 0 would be right here. And this is the one at pi over 3 and 2 pi over 3. Okay, so now if I put this in my graphing utility and I only put dy d theta in here, I get this graph to the right. What does this mean? Well, first thing I did is I put it in my calculator and I went ahead and put the 0 values right here so we knew where it was. Now, this is the graph of dy dx. My dy dx is changing from positive to negative. So if my dy dx is changing from positive to negative at that point, so it was positive and now it's negative, so it's increasing, then it's decreasing, that is going to be a maximum. Here at pi halves, it's going from negative up to positive. So that's going to be a minimum. And then we're not going to do that problem.